Hello, welcome back to Decaf-Math. So today let's go over the derivatives of trigonometric functions. Trigonometric functions. So let's focus on writing out what the derivatives are, and then we can build some intuition about why they are what they are. And this topic was requested by a viewer of this channel, so hello, and I hope that you find this relaxing and helpful. So, as usual, when we talk about trigonometric functions, we usually start with sine and cosine. And the reason is because when we look at a unit circle on the xy coordinate plane, sine and cosine are the two that we can actually see visually here. X is the cosine of our angle, and the y coordinate is the sine of our angle. The other four, tangent, cosecant, secant, and cotangent, are actually and can be written in terms of sine and cosine, and it's not as clear. You can't really see it so directly. So we'll start with sine and cosine. The derivative of sine x is cosine x, and the derivative of cosine x is negative sine of x. Okay, so we can just memorize these two. From these two, we could get the derivative of tangent x. This is secant squared x, which is secant x squared. And I'll show you generally how we can get this from these two. But let me just write out what the derivatives are. The derivative of cosecant x is negative cosecant x times cotangent x, and the derivative of secant x is secant x times tangent x. So when we squish things together like that, we mean times. And then the derivative of cotangent of x is negative cosecant squared x. Okay, so these are our six. The derivative of sine x, cosine x, the derivative of cosine x, negative sine x, the derivative of tangent x, secant squared x, the derivative of cosecant x, negative cosecant x, cotangent x, the derivative of secant x is secant x tangent x, and the derivative of cotangent x is negative cosecant squared x. Now, like I said, we can get these four from our first two, and that's because you can write each of these other four in terms of sine and cosine. Specifically, tangent x is sine x over cosine x, right? Cosecant x is 1 over sine x, so this is by definition. Secant x is 1 over cosine x, and cotangent x is 1 over tangent, which is cosine x over sine x. So basically, when we take the derivatives, you can notice that we're taking derivatives of quotients for all four cases. Something divided by something. 1 over sine x, 1 over cosine x, cosine x over sine x, right? Which means we can use the quotient rule for derivatives, right? So the derivative of each of these quotients will be in terms of the derivatives of sine and cosine, which we can just memorize. And then once we apply that quotient rule, we can use these definitions back to get the actual derivatives. So I'll show you what I mean with tangent x here in a second, but I wanted to just kind of start giving you that idea. But if we're just looking at these and trying to memorize them, I highly suggest, if you are in an actual calculus class, to just go ahead and memorize what these derivatives are. Because if every time you have a problem and you need to apply one of these, usually it's not just directly each of these, it's going to be applying the derivative of these, and you have to work with those, and it's going to get even more complicated, like maybe needing to use the chain rule or the product rule or the quotient rule again. So if you need to take all the steps to get just these derivatives in the first place, you might run out of time. But I wanted to just mention where these come from if you're the kind of learner that likes to know why things are the way they are. But for now, if you are in the calc class, just go ahead and take some time to memorize these 6 functions, the derivatives of these 6 functions, okay? One thing, if you are a pattern person, I can point out that knowing which ones are negative, the functions that start with the c, like cosine x, cosecant x, and cotangent x, all have negatives in their derivatives. And I also like to buddy them up or pair them up for patterns. So you'll see that tangent of x and cotangent of x have stuff squared, secant squared x and cosecant squared x in them. So tangent and cotangent are buddies in this way. And I can also pair, and cosecant and secant are kind of buddies in this way because it's stuff times other stuff. It's like itself, so cosecant, the derivative of cosecant x is itself, so negative cosecant x times something else, cotangent x, and the derivative of secant x is secant x times tangent x, so it's stuff times stuff. So I pair cosecant x and secant x that way. But you can also pair up cosecant and cotangent, because if you look at these two, the derivative of cotangent x is negative cosecant squared x, and the derivative of cosecant x is negative cosecant x cotangent x. So they're kind of buddies, and secant x and tangent x are kind of buddies as well. So they're kind of like all friends. But however you like to memorize it, take your time. It's a lot, it's a mouthful, but I promise that if you keep doing problems and you take time to just memorize this from the start, it'll just come naturally for you. So, and hopefully even just watching this video helps. Okay, so let me just work out an example of using the quotient rule to get these derivatives, just in case you were wondering. So first things first is memorizing these two. I actually haven't worked this out in a long time, but I believe it's sufficient to just use, well, it's always possible to just use the definition of a derivative. So remember, our very, very fundamental idea of a derivative is to take the difference quotient and take the limit as h, or the distance of the 2 points to approach 0. So we're finding f of x plus h over h. I'm going to take that limit. So for example, the derivative of sine x, you could probably set f of x equals sine x. You'll have sine of x plus h, and then you can use the sum formulas for sine. And I believe if you found that limit, you could get cosine x. If you're interested, we could probably do that proof in another video. I haven't actually worked this out in a long time, but you could try this on your own, or if you have any questions, comment down below. But I actually am interested now. It's been a while. But for now, you can just take my word for these two limits, okay? Or these two derivatives. But knowing these two, let's find the derivative of tangent x, for example, and let's prove that it really is secant squared x. So, to find the derivative of tangent x, we know that that's the derivative of sine x over cosine x. And since we have a quotient, I actually don't like the quotient rule, probably because I never really got used to using it. So I like to write quotients in terms of products. So normally I would do something like this. Okay, and then I'd go ahead and use the product rule on the inverse, but I don't want to be a bad example, so I'm going to use the quotient rule. Now, notice that we have something divided by something. So you may or may not be familiar with the little mnemonic, or I don't know if it's a mnemonic, but just a little trick here for quotients. So we have the top being the high, right, and the bottom being low. So it's kind of high and low. So we have low d high minus high d low all over low low. So like it's really like high over low, but high. Anyways, if that mnemonic means something to you, awesome. I've been using it lately, and if it doesn't, then I just sound silly and ignore what I'm saying. But basically, we're doing low d high. So we keep the thing on the bottom, the low. So cosine x times d high, meaning derivative of the thing on the top. So sine x minus high d low. So I'll keep the top high, d low, so meaning the derivative of the thing on the bottom, all over low low, meaning bottom squared. So cosine squared x. Okay? So basically, we're just using our quotient rule. So now we just need to plug in what the derivatives of sine and cosine are from the ones that we memorized, just these two. So the derivative of sine x is, so this equals, the derivative of sine x is cosine x. The derivative of cosine x is negative sine x. Okay? So we basically have cosine x times cosine x is cosine squared x. Negative sine x times negative sine x is positive sine squared x. The whole thing over cosine squared x. And then cosine squared x plus sine squared x, that is a trigonometric identity. And that equals 1 over cosine squared x. Oh, it's so beautiful. This mess just simplifies down to 1 over cosine squared x, which is 1 over cosine x all squared. Remember, because if we have a fraction squared, we can square the top divided by squared the bottom. And 1 over cosine x is secant x. So we have secant x squared, which we write as secant squared x. So, ta-da! So, like I said, we can get the derivative of tangent x, or each of these, using the quotient rule and using just our basic derivative of sine, derivative of cosine. But if you had to do this every single time you had a problem that involved the derivative of tangent, that might just take you way too long. So just go ahead and memorize these other 4. But I hope that this is kind of cool to see. I love it because it looks so complicated, but then it just works out. I love it. So when you do the derivatives of these other 2 here, you might have to split the cosine and the sine so that you get something, because remember, when we take the derivative, what we're going to get in terms of sine and cosine. So you have to use your original definitions of cosecant and secant and cotangent to write it back into these forms. So you might have to be clever in how you break that up. If you want to see these other ones, just let me know. But I hope that this gets you on your way. Take your time. If this is the first time you're seeing it, definitely take your time. Make flashcards if you need to. Just, at first, sometimes it just is a little bit tedious, but once you get it, it's in there. I promise, it's somewhere in there. So then the next step will be then to apply these basic derivatives of our trig functions to do problems like if f of x equals like tan 3x times I don't know, just trying to make up a problem, sine x or something like that. So in this case, because we don't have tangent of x, we have a 3x here, we have to use the chain rule, because it is tangent of stuff. It's not tangent of x, it's tangent of 3x. So we have to use the chain rule, but we also need to apply the product rule if we're trying to find d of dx of f of x, or f prime of x, as we often write it, right? F prime of x. We have a product here and we have a chain rule here, so this problem would get kind of messy, but we would definitely need to apply the basic tangent of x, the derivative of tangent of x. We would be using this. But remember, if we're finding the derivative of a product, we can't just take the derivative of tangent 3x and multiply by tangent of sine of x. So we won't work out this exact question right now, but I will tell you what it is not. This would be the sad answer. It is not tangent prime of 3x times sine prime of x. Okay, and even worse off, tangent prime of 3x, you might say, oh, tangent of x, the derivative of tangent x is secant squared x, so this is not secant squared 3x times cosine x. Okay, so if this is what you would have thought, that's not correct, but I suppose we can just leave that as a cliffhanger. I'm so mean, but just to get you started, you would use the product rule, and then you would also need to apply the chain rule for this part. Okay, let me know if you can get an answer for this. I guess you can call this a little challenge question, but if you have any other specific problems using these trig functions, let me know, and I'll probably include them in a separate video. I'm just gonna keep doing math to infinitum, so we can come back and do some problems here if you want, and I'll just kind of put some questions together. But remember, just for products and for quotients, you can't distribute the derivative, but addition and subtraction you can, and you can also pull out scalars. So don't forget your derivative rules, and I hope that this was helpful. Let me know, as always, if you have any questions, but here's a little start for these 6